So thank you all for joining today's Lunch and Learn Bright Solutions, Harnessing Solar Energy Through Snow Fences and Noise Walls, jointly hosted by the Office of Research and Innovation, Office of Environmental Stewardship, and Operations Division Blowing Snow Control Shared Services. We are excited to have Dr. Yang and Dr. Yu from North Dakota State University joining us today. We will have time for questions at the end of the session, so please enter them in the chat box throughout the presentation. Today's session will be recorded for those who cannot attend. If you have enabled your camera during the session, the recording may include your image, which is private data under the Minnesota Government Data Practices Act. You are not required to allow MnDOT to use your image, and there are no consequences for declining to do so. To opt out of the recording, simply turn off your camera. Before we get started, we have two announcements from our Office of Research and Innovation. First off, our funding awards for our academic research solicitation will be announced in late December. And secondly, over the past year, more than 30 MnDOT staff from across the agency have been working on developing MnDOT's innovation strategy, and that final report is expected to be published in late December. I would now like to introduce today's presenters. First up, we have Dr. Mijia Yang. He is a tenured associate professor at the Department of Civil Construction and Environmental Engineering at North Dakota State University. Dr. Yang has received his PhD in structural engineering in 2006. Before joining NDSU, he worked as an assistant professor at the University of Texas at San Antonio and was a postdoc researcher at the University of Nebraska-Lincoln. Dr. Yang has practiced teaching and research broadly in structural engineering. His research concentrates on impact and blast protection with advanced engineering materials, multi-scale modeling of composite and concrete materials, smart health monitoring in civil infrastructure, and self-healing concrete. Dr. Yang is currently serving as the associate editor of the Journal of Materials and Civil Engineering and has authored more than 100 publications, including journal papers, conference papers, and reports in the field of composites, structural engineering, and characterization. And now Dr. Yao Yu. He has earned 2 master's degrees and 1 PhD in architectural engineering, civil engineering, and computational science and engineering in 2008, 2012, and 2014. After graduation, Dr. Yu worked in the industry as an energy engineer. He is a LEED accredited professional and an ASHRAE building energy modeling professional. Currently, Dr. Yu is working as an assistant professor in the Department of Civil Construction and Environmental Engineering at North Dakota State University. Their full research reports and technical summaries can be found on the MnDOT Research Project database. So let's welcome Dr. Yang and Dr. Yu.
Thank you, Michaela. And thank you all my friends and colleagues at MnDOT. It's a great opportunity to share what we did for the harnessed solar energy through accessory structures of highways. So the presentation topic, we put it like this way, we call perspective, design, and potential implementation of solar noise barriers and snow fences in Minnesota. So this is a project funded by MnDOT. And first I want to acknowledge all the helps and contributions from our project panel members. Liv, Dan, and Josh told Kevin, Philip, right, and also Cole helped us to visit the site. Peter always help us to guide us on the noise analysis, and Susan and Brent. Okay, and I want to make a special thanks to Don, Peter, and Liv for guiding this project to the end. And also I want to appreciate the effort from our students. Yuan, Mel, and Garrett, Essen, Payman, and Mohan, and Aaron. We did a kind of systematic research from prototype of solar noise barrier and solar snow fences to the circular design and to the prototype testing. That's what we did for this project. For today's presentation, I want to put it into 6 tasks. First, I want to talk about the survey we did, focused on acceptance of public on harvesting energy from rights-of-ways through solar noise barrier and snow fences. Then we talk about the prototype design of solar integrated noise barrier and snow fence system. I'm happy to report to you we have field implementation in Wyoming, which looks very nice. I will show you some photos for that. And also we want to talk about potential safety effects or concerns of the solar noise barriers and snow fences when we used on the highway. And also we want to talk about utilization or storage of solar energy produced, how we can integrate it into the power grid, or even in the future we can store it in the battery. Then the 5 topic we'll talk about cost benefit if we want to implement such a system in Minnesota. How does it look like in terms of financial perspectives. Then we talk about the next step. Okay, now we have some initiative in the United States. Some states already did some solar projects along the highway, but not same as what we did here with MnDOT. We have one solar area, which is more like a solar farm, which put it close to a highway, right, but not integrated into the highway structures. And one is on the Interstate 205, the other one, which is in Ohio, on I-280. Basically is a standalone solar farms, right? Our purpose for this project is to integrate such a solar system with the highway accessory structures like noise barrier and snow fences, so that we can achieve 2 purposes through one system. Okay, so we did a survey through utility companies, and we reached out to 91 utility companies, and 21 responded, which cover municipal, co-op, and distributor and utility companies, right? So basically, we ask them several questions. First question, whether they will be interested in purchasing the solar energy we generated through such a system. The second thing is we want to ask them, are they be able to construct such a system? And also, is there any incentive or insurance program associated with that, right? We look at the general plot here. We see the blue ones indicating kind of yes answers to those questions. We see, pretty much half, right, to support or are interested in such, a project. Most of the companies, they have the capability to build and integrate those systems with the power grid. And in terms of incentive and financial support, there are some, but not much in terms of that. And also we look into, particularly we look into one question, which is, will your company be interested in purchasing the solar electricity generated through the MnDOT solar snow fences and snow barriers? We see this pie chart. We see pretty much half, right? Yes, 14, depends 38. The most concerns are, depends on the price, right? And depends on the scale of such a system. So those are the feedbacks we collected from utility companies. And also we did a survey through general public. We reached out to 111 churches near the highways. We saw those are the people always visit, and we have 56 response. So the question we asked them, what they support the idea of using solar panels on the noise barriers along the highways, and also are they interested to utilize or purchase such electricity generated, and also if the transportation dollars are used to install and build such a system, are they supporting that, right? And sometimes when we use this system with a noise barrier, it will affect the functions of a noise barrier. Are they still being support and being able to support that? Now we see the response quite positive, right? If you look at the blue bars, which is much higher, more than half is supporting those ideas. So the summary of the comments from the public, which is, this is a great idea, good idea, and even though sometimes it may affecting the appearance of that noise barrier a little bit, but it's acceptable, and also they're interested to use such an energy in the home or for other purposes, right? But some concerns, which is, who gets the energy, who pays for that, right? That's always a concern for general public, and this could be discussed if we implement it. And also, we served the landowners, right, through a purchased software, commercial software on the landowner database. We found landowner name and address. Then we did a phone interview with them. We interviewed about 20 landowners, which is we see whether they are supporting to use the properties for storing the snow, right? If we put a snow fence around their properties, and also are they interested to have a solar snow fences in their properties and generate and purchase the energy generated, so those things. And the response we got, pretty much half, right? If we look at the blue bars here, they are supporting that. There are some concerns, right? One of them is, such a system may affecting the farming practices, right? And some concern about the prices, of those electricities, and do they have any incentives if they give the permission to install snow fences along the properties, right? So those are the comments we have. So overall, the comments are supportive, and such an idea is welcome through the utility companies, through the general public, through the landowners. So the next phase in the project, we talk about how we can prototype such a system and eventually integrate it or install along the highway associated structures. So first we look at the solar noise barrier structure. Particularly we are thinking, we're recommending a kind of a bracket with strut type of configurations, right? So such a configuration can easily connect into the posts, and also can have functions that can adjust the strut and change the orientation of the solar panels. So this is for the noise barrier. For the snow fences, we can mimic the existing snow fence structures. We just replace the plastic strip we currently use and replace it with a solar strip. And basically, we want to achieve two purposes, right? One purpose is to harvest the energy. The other one, which is serve as a traditional snow fences. And the good thing is, I want to bring the news to you. We recently worked with Landboard Power LLC. We are doing a project funded by NCHRB IDEA, which is implemented in Wyoming. So those are the snow fences, which is we put in place. You see here, compared to the wooden snow fences, right? The aesthetical point of view of those solar snow fences is much better, and also it has those solar strips inside it. It can be made into monofacial or even bifacial that can increase the energy harvesting efficiencies, right? Now, and also we have a motor behind it that can change the orientation of such a panel. So those are the prototype of, both of the system, and we want to evaluate how does such a system, when implemented, how do they affect the intended functions of the solar noise barrier and solar snow fences, right? So first we want to look at into solar noise barriers, how much the noise reduction could be affected by such a solar system, right? We know the noise reduction for a noise barrier comes from two parts. One part is a proportion of the noise barrier panels. The other one, which is the elongation of the transmission paths, right? And this is the theory of that. Now, if we have a noise barrier, separate the traffic with the residential community, which is we kind of increase the path of the noise travel, right? That could reduce of that. The second thing is absorption properties of the noise barrier panel. And we did several simulations. One of them is for traditional noise barriers. That's the currently used by the MnDOT, which we pick a segments along the I-94 in Moorhead region, which is we have two sides of the noise barriers with the receivers on the two sides. What we see here, if without barriers, we have 72.2 and 70.4 decibels on the standard level, right? And this is not, it's over the permitted noise level for communities. Now, if we put the currently using noise barriers, where we can reduce the standard levels to 55.9, which is the noise reduction pretty much come to 16.4 or 18.6 for the two different locations. And if we use the solar noise barrier with less absorption properties, if we change that, right, which is we can see his noise reduction level has been reduced, but not much, with only about 0.2 compared to the traditional one. So this is one. And also we did one single noise barrier, after discussing with Peter, and we have one barrier here, we have two-way traffic here, and we have 6 receivers at two sides, and we give the absorption coefficients. For the absorption material, we have 0.9 that can be absorbed, and for concrete block, we have 0.3, 0.4 as the normalized absorption coefficient, and glass we use very small ones. If we do that, we will see, right, for those 6 receivers, we see the maximum difference of the decibel. Yes, the solo noise barrier will reduce the effectiveness of the noise barrier, but with a small magnitude, right? The maximum is about less than 2 decibel, right, for all the receivers, right? Most of them are around 1.5 decibel in the magnitude. And also we did a snow drifting simulation for the solo snow fences, which is, we have snow fences at 40 location, right? So this is just a mark, in terms of feet along the along a cross section of a highway. We see, right, this is the windward, this is the leeward one. We see we can capture the profile of the snow drifting, and also we can find the maximum height and the spreading width of that, and for different porosity and different bottom gap distances. And we compare that with different terrain profile and also with Dr. Tabler's empirical equations. Actually, both of the results are pretty consistent with each other, and also we can see the profile has a small effect on the snow drifting profile as well, right? If we use a typical road profile with the ditches on the two sides, and this one is going to, right, reduce the spreading width a little bit, right, but doesn't help reducing the peak drifting height. And if we have a flat one, basically what we see here is, the spreading width is a little bit higher, and also the peak height of the drifting is a little bit high too. If we have, the solar snow fences alongside of up here, that could change that too, right? Which is basically he can reduce the maximum drifting height a little bit. So those are the results we got from the snow drifting simulations. And also we did one for the solar growing modeling, right? Because if we put solar panels along the highway and we have sun year-round, that might cause problems for the drivers and disruption to the traffic. So we did one simulation. We say if we have, if we install a solar noise barrier with 15 feet high, right, with a length of 1 mile along the I-94, we did a solar gradient simulations, and the receiver location is at feet, right? Which is we try to mimic the drive location, the eye level of a driver, and we did simulation every 4 seconds. And through that simulation, we find the glaring is minimum in 1 year, right? If we summarize all the glaring events, it's about 231 minutes in 1 year, less than 4 hours in 1 year. Even for the cases without sunglass protection, right? If with sunglass protection, we recommend that the solar noise barrier will not cause disruption or uncomfortability to the drivers or the traffics. So, and we said for our solar system to work, the electrical portion is also very important, right? We do not want to have an unsafe electrical system along the highway. And so we compare the existing solar system that currently in the market, right? One of them is for residential application, one of them for commercial application at different scales. Both of them using higher voltage kind of interface with the external usage. The first one with 240 AC type of output. The other one, which is with a 240 DC output. Both of them, the voltage is pretty high, will cause potential damage to any persons who has, access to such a site. In our system, we develop a so-called smart wire techniques, which is we can use modularized connections. We can use 3 or 4 panels that are connecting together, and each panel will have low voltage output. And through that system, we can connecting them through one controller, one inverter, right? And then we can, through 3 or 4 groups together, we can reach to the needed, power grade voltage and frequencies. So the whole system will divide into 3 stages. First stage, which is directly conversion of the solar panel to the DC voltage, right? The second one, which is a transformer or inverter, right, to convert the DC to AC. The third one, which is kind of regularize those AC signals to the 60 Hertz frequencies with 110 voltage output, so that can be integrated into the power grid directly. And if we have any cases that one of the solar panels is broken, right, maybe through the crash or accidents happened to the solar system, and since we use 3 or 4, each of them which is utilized in a low voltage level, then if one of them is broken, the remaining solar panels can be kicked up and still keep their 110 voltage output and 6 Hertz frequencies, that the system still can be used without any discrepancies. And we built this prototype in the lab, right? We tested it through our circular system in the lab and outside for the ambient light. So this is the 3 panels we connecting together, and each of them we are connecting with one controller, one inverter. And through our payload, through resistances, we can connecting them all together and showing in these oscilloscopes. We can see we reach the desired voltage and frequencies. And also we did one under the ambient sunlight, and it proves the output voltage and frequencies and reach to the level we want. Right in here, in this oscilloscope, we see the AC signals has been generated. For one of them, it can reach about 32 voltage, and also has output frequencies close to 240 to 250 watts for the performance of each panels. Right? If we integrate this system to the highway associated structures, we anticipate it can be integrated very well and perform the intended functions. Now I will have Dr. Yu to join on to talk about the cost-benefit analysis of such a system.
Okay, thanks, Mijia. So I will take from here and talk about the cost-benefit analysis results. Since we are looking at the installation of a PV system on both noise barriers and snow fences, at the beginning, we developed the cost-benefit model separately, including a model for PV system itself, a model for noise barriers, and a model for snow fences. And then we integrated the PV system model and the other corresponding model together. For example, the noise barrier model or snow fences model. And depending on we are working on PV noise barriers or snow fences. So in the end, sensitive analysis were conducted to evaluate the impact of the different parameters in models, and especially critical parameters on the cost-benefit result. So the associated cost and benefits included in the PV system model are shown on the slide. For example, the cost includes direct capital cost, indirect capital cost, operation and maintenance cost, and the future cost. So the benefit of using PV systems, including incentives from the government or local utility companies, RECs, revenues, by selling the electrical power generated to the to utility companies, or the electricity cost savings by using the power on site by MnDOT, as well as any social environmental benefits such as the reduction of greenhouse gas emissions. So on this slide, the table down here shows the 5 critical factors considered in the model development. It depends on we are looking at the installation of PV systems on new noise barriers or snow fences or on existing ones. It also depends on ownership. Who will invest and own the PV system? MnDOT will have the direct ownership, or a solar developer will have it through what we call the PPA, Power Purchase Agreements. In addition, it also depends on how to deal with the electrical power generated by the PV system. Sell it to utility companies or use on site by MnDOT, for example, to provide power to the streetlights or facilities in the rest area on highway. So besides, we will also look at the size of the project. For example, to install PV panel, PV system on 1 mile noise barrier or 1,000 miles of snow fences. Incentives or any other social or environmental benefits will play a significant role. So we also look at the possibility for incentives or other environmental benefits and consider or not to see how they will affect the results. So next one, please. So on the previous slides, we talked about the PPA. So let's look at PPA here. So PPA is a financial mechanism that allows MnDOT to accrue the benefits of a solar power, but without owning the system. So this means a third-party company, and we call the solar project developer, and it will procure, builds, operates, and maintains the solar system. And MnDOT buys power from them at negotiated rate. So under the PPA, so the rate could be equal, lower, or higher than the current price of purchasing electricity from the grid. So the list on the right and shows the potential solar developers we found and for PPA in Minnesota. And this map shows the excuse me. This map shows the service territories of these solar developers identified, and most of them investor-owned utility company. So before we talk about 5 different critical factors. So to consider this, these factors in the model, and we have 10 case scenarios to be analyzed at least here. So it's shown cases 1 to 4 involve selling the generated power to utility companies. And in these cases, we need to connect the system with the grid. In cases 5 to 8, we will self-use the generated power by MnDOT to, for example, streetlights or other facilities in the highway. And in these cases, a separate battery system is needed, and which will further increase the initial and operating cost. So in cases 1 to 8, so as you can see there, the PV system is owned by the MnDOT. But in cases 9 and 10, PPA, the power purchase agreement, will be used, and MnDOT will not own the system but buy power from solar developer. So this slide visualizes the installation of a 4 feet by 8 feet PV panel on a 20-foot tall noise barrier walls and a PV snow fences, where customize the PV panel with the size of 12 feet by 0.5 feet installed on an 8-foot tall snow fence.
Dr. Yu, it looks like you might have accidentally been muted.
So how about now? Is that okay?
Yes.
Where are we last time? I can't remember. So here?
Yep, we heard you complete this slide.
Oh, okay. Sorry.
No problem.
Yeah, so if we're looking at this slide, so since we developed the cost-benefit model one by one, so let's first look at the cost-benefit results of the PV system itself, not including the noise barriers or snow fences. So here are 3 different types of results were considered. They are payback period, for short we call PP, net present value, NPV, and internal rate of return, IRR. Next one. So this is the result in terms of net present value, payback, and IRR, and for the PV system to be installed on 1 mile noise barriers on the left side of the slides, or on 1,000 miles on the right. So the rank, as you can see, the last column of each of the results, from 1 to 10, based on the net present value. So for net present value and IRR, internal rate of return, so the greater the value is, the better. But for the payback, the less the better. So as you can see, case 10 is the most cost-effective case for 1 mile solar project. And when the project size increases to 1,000 miles, and case 4 is the best one. So which has the payback of around 10 years. And also the longer the length and the more cost-effective the project. For example, from 1 mile to 1,000 miles, the payback has been reduced. And also compared to cases 5 to 8, so cases 1 to 4 are more cost-effective. So this means that it is not cost-effective for MnDOT to self-use the generated electrical power and compared to selling the power directly to utility companies. Next one, please. So this slide again shows the different case scenarios. And if you click there, so this is the case 4 and case 10. You can click. Yeah. So again, cases 1 to 4 sell power to utility companies, and 5 to 8 self-use it. And cases 9 and 10 are through PPA, the power purchase agreements. So where case 10 includes the social or environmental benefit, but case 9 does not. Next one. Okay, so similar results were obtained and for the PV system to be installed on snow fences. So 1 mile is on the left side of the slide, and 1,000 miles results on the right. So for example, case 10 is still the most cost-effective case for 1 mile solar project, and case 4 is the best one for 1,000 miles. And from 1 mile to 1,000 miles, the payback has been reduced, and the cases 1 to 4 are still more cost-effective than cases 5 to 8. So after the results, only for the PV systems. So let's look at the results after the model integration. So for example, considering the installation of PV systems on new noise barriers or snow fences, or on existing noise barriers or snow fences. So this means the PV system and noise barriers or snow fences are going to be built and financed together as a whole project. So let's start with the result when installing PV system on new noise barriers. So still 1 mile solar project result is shown on the left, 1,000 miles on the right. So as you can see, case 10 is still the most cost-effective case for 1 mile solar project, and case 4 is still the best one for 1,000 miles. But the payback is increased. For example, more than 25 years for 1 mile solar project, and more than 22 years for a 1,000 mile project. So the corresponding IRR, the internal rate of return, are also low close to zero or even negative. Again, for net present value and IRR, the greater the value is, the better. But for the payback, the less the better. So this means that when integrating these two cash flows together, one of them is the model for the PV systems. The other one is the model for the new noise barriers. The results are significantly influenced by the cash flow of the noise barriers because the capital cost for the noise barriers is much higher than the cost for the PV system. So this slide shows the result when installing PV systems on existing noise barriers. So as you can see, compared to the new noise barriers, the payback is reduced and the IRR is increased, especially for the 1,000 miles of solar projects. And this is because we are looking at existing noise barriers whose installation costs are not counted in the integrated cash flow model. Next one. So this is the result when installing PV system on new snow fences. So still case 10 is the most cost-effective case for 1 mile solar project and has the payback of 4 years. And case 4 is still the best one for 1,000 miles and has the payback of 7 years. So this is because when integrating these two cash flow models, means the model for the PV system itself and the model for the new snow fences, the results are mainly influenced by the cash flow of the snow fences and due to the significant benefit of using snow fences. So the table down there and shows the benefits and due to the use of snow fences. So in the model. So this slide eventually shows the results when installing PV system on existing snow fences. As you can see, compared to the new snow fences, the payback reduced to 1 year for case 10 in 1 mile solar project and to 4 years for case 4 in 1,000 miles project. And this is because, again, we are looking at existing snow fences and whose installation costs are not counted in the integrated cash flow model because they're already there. We also conducted analysis to the sensitive parameters, at least in the table here. For PV noise barriers, we consider 17 parameters, and for PV snow fences, and there are 15 critical parameters. So I'm not going to discuss the results one by one here in detail because the limited time for today's presentation, but you may find the corresponding results in the published report. Okay, let's look at the summaries and conclusions of the study. So in this study, acceptance of a public on harvesting energy from right of ways has been surveyed and summarized. A solar panel integrated noise barriers and snow fence systems has been designed, built, and tested in the labs. So potential safety, effect of the system has been tested, including noise reduction, solar glaring, snow drifting, and its impact collision responses. And then a smart weather technology on integration of solar energy with the power grid has been tested in labs, and also under ambient solar light. So by adding PV panels, PV system on noise barrier, it will shorten the payback period of a noise barrier project. So that's make it more cost-effective and attractive. And for a structured snow fence, and usually, they are not going to be used in summer. So the installation of the PV system on them will add more value to the structured snow fence. And also, it will be good for the environment because of the generation use of renewable energy. So, so more cost benefits conclusions shown on this slide. So, for example, installing a PV panel on 1 mile of a new noise barrier and it's not cost effective. So therefore, so it's this type of application would not be a cost effective option for the agency, for MnDOT. But installing PV panel on 1 mile of existing noise barriers, especially through a PPA, the power purchase agreement, would result in a minimum upfront cost with nearly 0 years of payback. So this suggests that this type of application would be a cost-effective option for MnDOT. The same thing, a PPA for PV panels installed on 1 mile of new structured snow fences, paybacks in 4 years. And even though environmental and social benefits are not included in the analysis. So this type of application, again, would be a cost-effective option for the agency. And a PPA for a PV panel installed on 1 mile of existing snow fences, paybacks even 1 year. And so again, this suggests that this type of application would be a cost-effective option for the agency. So for the PV noise barrier snow fences, the longer the length, the more cost-effective the project. So therefore, 1,000 miles or 100 miles or even 10 miles project, PV noise barriers or snow fences project that has a shorter payback period and it's more cost-effective compared to, for example, 1 mile project. So under this project, we also develop we call the cost-benefit calculator. So the interface is shown here on the left, and which allow us to use a wizard as shown on the right to evaluate the cost effectiveness of a PV noise barrier or PV snow fence project by entering parameters like that. So the output result is like that as shown down there, including the results of net present value, payback, and ARR, along with the curves. So the calculator and user guide can be downloaded from this link below. Next steps, excuse me. So we are now seeking funds and opportunities for a demonstration project. For example, 100 feet, the PV snow fence, and with the cost of about $290,000, including the cost of materials, design and development, and as well as a field setup and tests. So the purpose is to further prove the feasibility of the solar project in both technical and financial ways. So in the meanwhile, we're also looking into the possible ways to utilize the solar energy generated by the PV snow fences or PV noise barrier, for example, for lighting of rural intersections to integrate with the power grid or farm irrigation systems. Okay, that's the presentation, and feel free to let us know for any questions, comments. Thanks for your time.